My name is Andrey Kudryavtsev, and welcome to my first session today. Let me reintroduce myself. So I'm a solution architect working on non-volatile products, mainly focusing these days on Optane, but the area of my conversation today with you is not just about Optane. So hopefully I will not lose my voice completely. I'll try to speak loud as much as I can. Please forgive me. I'll be speaking about Optane, non-volatile memory technologies, what we are doing in the NAND business, what we are doing in the different form factor businesses. Let's start from that. So, as usual, info disclaimer, updated version. I will start from basics and go down deeper, because basics can help us to understand why Intel is doing exactly what it's doing in non-volatile memory business right now, and what our current strategies and priorities. Some of you may be already familiar with our products, but basically the overview and the overall look why we are doing that is really important. So at some point at the time, and obviously that happened a long time ago, before the product development started for such technologies like 3D cross-point technology and Optane technology, we realized there is a significant gap between different media tiers, between what memory can deliver, between what storage can deliver. And that was the case for years, and obvious that we have to do something special to do that. So in order to address that, about 10 years ago, in 2008, Intel introduced first SLC-based product for data center, X25E, really successful commercial SSD, which was widely available with us and produced by us with our NAND technology at that time. And since that time, we got lots of evolution and innovation into the NAND-based SSDs. And well, you know, it's not just a single innovation curve or single achievement that you did once and you reuse it. With its SSD business, you have to innovate constantly. There are multiple reasons to that, so I'll be talking about that later. What causes us to innovate more and what forces doing
Andrey,
that.
I understand the capacity gap for DRAM,
Yeah.
but I'm trying to understand the performance gap between NAND SS. Is it because it's not as fast as DRAM? Is that?
Well, there are multiple reasons to that. If we say, like, let's say 6 years ago, interface was a problem. So saying like SATA or SAS interfaces by the definition designed for the technologies developed 30 years ago. So with all the stack of SCSI commands, all the stack with HCI commands. And that was the case that, first of all, the common stack was so huge, and the latency of the protocol itself was very significant. So the first that had to happen to improve the performance is to improve their communication protocol. And that's how all NVMe story came up with NVMe Express protocols and with evolution of NVMe Express protocols too. So, you know, there are multiple versions of NVMe Express protocols, which is constantly evolving. But the overall problem was not only with interface, how storage is connected. The overall problem was with the media technology, because media technology cannot reduce the latency. With NAND, you know, we limit it with how we address the media component. And every time we do a new NAND product, I will show that for sure today in the QLC business, we had to do a lot of different things to improve the product performance. Not necessarily new NAND technology helps us do that. In fact, today, we've moved into the QLC story. We see that the performance of the media, it's not growing. Actually, it's degrading, and you will see that because capacity is improving significantly, and the technology is evolving. So we have more data to address, and NAND is limited to do that. So cannot reduce latency, can grow capacities. That's a great thing about that, but latency is limited. So to move that forward, we came up with the idea of using different kind of media technologies. Of course, there are many speculations about 3D cross-point overall, especially when it appeared about a year ago in the market and available in the market since then. But we always had in mind that 3D cross-point technology, Optane technology, is developed with special mindset. It's not just a special media, as you know, that is X number of lower latency and cache line addressable, the whole idea of behind that technology that we can use it for different needs. And one of these needs can be storage, and I'll be speaking today about that, how we use it actually today with storage and how software companies innovating, reusing it in the different environment. And another idea in mind, we always had it in mind, to use it as a memory replacement, as memory addition or replacement, depends how you see that, with Optane TC persistent memory, which is the new marketing name, to the product which is based on the DIMM form factor with 3D crosspoint media on it. But that's not just enough. Having only Optane technology-based products in the market for us, it definitely doesn't mean that we will cover all use cases, especially the use cases where we want to enter to the hard disk market, where we want to say, well, we want to go deeper into what is typically used by the hard disks, and we want to provide the cost-effective solutions to customers which are reasonably well performing, or amazingly performing, honestly, but still very cost-effective. And so I'll be talking today about what Intel is doing in the QLC NAND-based SSDs. And not just that, because to me personally, I see integral part of a QLC is transitioning into their different form factors, such as what used to call the ruler, now it's called EDSFF form factor, because that's something, that's like a solution bucket that can help you to reduce the cost of your storage and go down to the cost that previously were really prohibited. So not one solution, many solutions, and that's the whole idea about Intel non-volatile solutions group, how we develop our strategy, because we go in two directions simultaneously. Well, multiple directions, especially in the form factor innovation, but from a media standpoint, it's always Optane on one end and NAND on another end, and it's not going to be changed. So let me move forward and give you like a basic idea where we see different SSDs by the kind used in different segments. Well, here I'm taking like a standard enterprise. It's because there are so many segments here. It may look like more like a type of a cloud business, but basically what we see here on the chart, it's applicable for many areas, including my own area in high-performance computing, because it's very much the same. So obviously, there are different sets of requirements needed for what we have in the client compute server, what we have in the storage segment, and well, if we look in the cloud, for instance, as a use case, so for object storage, we consider obviously different kinds of products needed for different needs. Like with QLC media, which is capable to deliver lower cost per gigabyte and attractive performance. We really trying to move to the market where we store the data on SSDs constantly, while Optane is still there, and Optane has significant play in object storage overall, to be used as journals, metadata, to be used as a cache inside the storage. That's very typical use cases for Optane combined with NAND-based technologies for actual general data placement. In the same way, in the server environment, in the compute environment, there are different kinds of requirements where we would say, well, it makes sense for you, for instance, for local storage or for local cache to use NAND-based SSDs or Optane-based SSDs. Again, depends by the needs. There are certain needs, like can be reasons for latency, can be reason for endurance, which is one of another attractive points for Optane SSDs. In the same way, it can be what's called today memory expansion or extension, and that's one of the products that I'm working on called with Intel memory drive technology. So this is a software product that allows you to increase the system memory by having Optane SSDs inside the system, so converting block device to a system memory, basically. I will have some material for you about that, but in general idea that basically that's the cost-effective way to introduce cheaper memory for the environment that needs to have expanded memory. And there are many cases such that, so like in the virtualization where you would benefit of having more system per compute, or in HPC environment where you can do that in big data, where you really need more memory to put the data inside the memory.
So in this scenario, I don't see any place for Optane DC.
Of course. Just to be honest with you, because Optane DC persistent memory, as you know, is coming by the end of this year. So I'm not sharing really much about what we are doing in that space. I do have some material for you. I have some, not much. Have some because technology is not yet introduced publicly. We do have certain engagements with especially software developers, because this type of technology, it has to be enabled by the software to get the best advantages of that. And of course, in the name it is, so it's persistency. So to take the advantage of persistency, I will share you ideas how you can start developing right now for this technology, even not having that technology available for you. And finally, to close that, our group is doing a lot in their accelerating their software business. So we have our software development folks in our organization who are doing development for a CAS acceleration solution, who are doing development what's called RST, Rapid Storage Technology Enterprise. So that's a traditional software RAID that we produced for years, but now it's optimized for NVMe. We also aligned with the platform technologies like VMD. You probably heard about that. It's one of ingredient in the latest Xeon Scalable processors. And of course, what Anu will be presenting later after me, that's everything about SPDK stack. All right, so let me go quickly into Optane, just to some of you to remind what Optane is. To some of you, maybe first time introduced, so feel free to ask any questions because, well, in the first look, that may really look busy, but I'll try to make it as clear as possible for you. So obviously, then we put Optane technology onto the block device, which is Intel Optane data center SSDs like P4800X that you have here on the slide. It's NVMe compliant SSD, so it's NVMe Express protocol. That means it's a PCI Express designed SSD. It's block addressable, so it's addressed by the lower granularity that you can address is 512 bytes, which is usual for storage. You can do a 4K addressing if it's needed. You can do variable sector size, but using advanced media technologies, which is built on and being a cache line, media being cache line addressable, it helps us to simplify a lot their SSD internally. So to make it really, to make the controller ASIC streamlined and to make it very optimized for the needs of the storage. So what it gives you first, the lower latency of the media and balanced performance between reads and writes gives you basically predictability of the performance. So your latency is not going up or down. Your average latency, or actually your max latency, is like a flat line, and that's the most significant difference with NAND-based SSDs. So as you probably know, with NAND-based SSDs, there are many additional overhead that controller has to do to manage the media, because the way how it's addressed inside the media, blocks, pages, erase blocks, these basically Optane SSD is free of that. They don't do that. So we don't have additional overhead. Their latency of their media component is very low. So on the device level, we can work in their sub 10 microsecond latency on a 4K random I/O. Just to give you an idea, so for NAND-based SSDs, that would be at least, well, it's about 10x more. So it's about 100 microsecond latency on a 4K.
So let me try to understand the graph here. At a write workload of roughly 700 megabytes per second, you're also doing read activity, and you're measuring the read response variability.
Correct.
And at that point, it's roughly a millisecond for the read activity response time? For
NAND-based SSDs, yes.
and in a comparison, you've got a standard SSD, which is I'm trying to understand what. So the black line here, the wavy line, is the standard SSD.
Correct. So
and the Optane is sitting here as a flat SSD.
Correct. It's this one, blue. Yeah.
And it's 0 microseconds? Is that?
Of course not. But on
the
this
scale
range,
here, it's
you basically you don't see that. The most important here that let me explain how that happens. So these steps in
How does that
yellow,
happen, Andrey?
it's a write pressure that we put onto the drive. Sorry?
Yeah.
Yeah, it's a write pressure that we put into the drive, and for NAND-based SSDs, that forces all background processes to start more active. That basically disturbs the reads, so your read latency is starting growing up, and it's not just going up linearly. It starts to have really deviation because you have to serve first of all your background processes, which are responsible for all your write operations. So to do erase cycles, to do that data movement that's needed for NAND-based drives. For Optane, it's not needed. That's why it's flat. It doesn't really matter what write pressure you put onto the drive. Of course, read performance is changing, but it's changing like within the same budget. Let me give you an idea. Let's say roughly you have 500,000 IOPS per second for 4K. And for Optane SSD, it's 550K IOPS for reads, and about the same for writes, 550K IOPS for writes. It doesn't really matter what you do, reads or writes, because if you do 50-50 reads and writes, overall you will see 550 again. If you do 70% writes and 30% reads, again, overall it will be 550. That's the beauty of the technology, because I don't really need to think how I'm writing to the drive and what's the mix ratio between reads and writes.
Again.
So I mean, the latency variation on the reads comes, they're wear leveling and garbage collection.
Oh yeah,
yeah.
Standard SSD stuff.
And so if you make a request for the data that's being moved around, you have to wait for it to be moved before the SSD can give it to you.
Yeah.
And Optane SSDs don't do that kind of wear leveling and garbage collection?
So they write effectively without any problem.
There is no that definition at all, because the media is cache line addressable. You don't need to do that. All the wear leveling and data movement happening because you have to do erase cycles. Right. And erase page for NAND is significantly bigger than the page that you read. The page that you write. So you have to combine pages together, do array cycles, and that's a standard NAND theory. And that's the reason why they've changing offer different workload parameters. Your performance is changing. Here, it's just the same budget. Also, if you look to that from slightly different perspective, now let's say, stick to the number, 550,000 IOPS for 4K random IO. On the device side, on the sequential performance, our SSD, this SSD, P4800X, it's 2.5 gigabytes per second. So 550,000 multiplied by 4K, it's actually, well, it's about
2.2 gigabytes.
2.2, which is actually write performance of SSD. Yeah. So now it doesn't matter at all what type of operations you are doing to the drive, because if it's sequential, random, the performance of SSD is not changing. It's the same performance budget that you have to just manage, but overall it's not changing, unlike with NAND, where your read performance is that and your random write performance is that low. That basically means we can put it in a very tough environment. And this case here, it's a standard caching case. So where you have workload which is constantly writing data on the drive while reading from the device. It's a standard caching solution, like in VSAN that I'll be talking later. Endurance. One of significant announcements that we did about a couple of weeks ago, let's say 3 weeks ago, we increased endurance of our Optane SSD, which was originally announced at 30 drives per day a year ago, and we were shipping these products with 30 drives per day. Now we are shipping the products with 60 drives per day. So basically, it's the same product, no changes to the product, no changes to the price of the product. It's just coming with 60 drives per day. And that is a natural improvement that happened to the media. And we realized that we can open it to every customer.
That for all customers, so also the customers that already bought into it? Or is it just for the new ones?
That's coming with firmware update. And depends on your current SSD condition. You may be eligible for that or not. And obviously, I don't need to compare with NAND-based SSDs because NAND is limited, and the P4600 SSDs that I have here limited by $3 per day. It's a mid-endurance SSDs, and there is no line of sight of having high-endurance SSDs in NAND business because it's conflicting the way that the TLC and QLC developed. So there is no type of these product capabilities in the QLC, for instance, media or TLC media to go to high endurance. You can over-provision any NAND SSDs to the depth, so like put many additional spare area that some customers are really doing, and that can help in some extent. For instance, if you over-provision NAND-based SSD by half, maybe you can go from 3 to 6 TB per day, depends on the workload. But in general, you're not improving the quality of the media. You stay within the same erase cycles available, and you only put the spare area to the drive that can help within some limited range. All right, and I'll be talking about the cache on my next slide. And please, okay. VSAN, one of the typical examples that we're really proud with Optane, and the first part of my presentation I'll be speaking about what we currently have. The next is what's possible to do. So both of these really exciting. VSAN has happened significant time ago, and it's available from different OEMs today as a qualified solution. Basically, what we are doing, we are using Optane SSD as part of our VSAN write buffer that is required for all flash solutions where you have, let's say, a number of NAND-based SSDs for your generic storage, and you want to put some write buffer on it to improve their operations. Different kind of operations. Usually, of course, because it puts all your writes, it's basically makes them sequential. So you put all your random writes to the Optane drive, and then you sequentially move that data to your VSAN cluster. That helps many type of enterprise class workloads. One of them is just TPCC-like workload, which is heavy both pressure for reads and writes. And we just showing that this type of investment into their hyperconverged infrastructure is key to their I/O performance. And because this is a relatively small investment considering to their software licenses, considering to the overall hardware cost. So basically, you need only one write buffer in your compute node. But the performance improvement is extremely significant. It's even more makes sense when we are moving to the cost-effective technologies like QLC, NAND-based SSDs, where you want to have that type of a buffer that can aggregate all your random operations and make them easy for QLC media. That helps everyone. That helps QLC to last longer because now you can rebalance your storage activities with some incoming buffer. And having Optane with especially $60 per day, you don't need to have high capacity. So like capacity of 375 gigabyte SSD is enough for that. We're really proud of that. Obviously, there are certain cases where we can leverage the low latency of their Optane SSDs, especially in the enterprise market. And one of the really the most common examples for SLA-related workloads is a database workload. So here we have an example of MySQL workload. And by the way, you can try that by yourself. So we do a lot to promote Optane technology to the market. So we have a website called tryoptane.com. I have a link after that. And you can go to that website and you can select from the predefined workloads which one you want to run at the moment. And it will run on the actual system with Optane and give you data in real time. So one of these workloads is that workload with MySQL. And basically it compares two systems side by side. One system is with 52 terabytes of available DRAM, and another system has a really reduced size, so like a 256, and has a lot of Optane to help in this replacement of their DRAM. So idea with MySQL that basically it can spin down to the storage media, and with Optane you can get really great performance for less money, and that's supported with TCO, and that's supported with real system configuration. So you don't need to go to high capacity of your system memory for this type of workloads where you know that it can effectively use storage. And another great use case, I have really many use cases because that's what our team is doing to promote Optane solutions is in big data. That is especially with Apache Spark. We run like a standard benchmarking configuration of that, and we run it in two ways. One way is we have only a DRAM-based system, and another way we have a compute node configured with Intel memory drive technology, which I will cover slightly later in all details. But basically, Intel memory drive technology is a software product which sits under operating system, and it can represent your operating system new system memory, which is a combination of DRAM and Optane SSD in the platform. So you are no longer limited by the hardware capabilities, how many DRAM sticks you can put into the platform. You are not limited by the processor that you use. And you can plug as many SSDs as you have slots in your platform and get really expanded memory. And we go up to, let's say, 24 terabyte in a dual socket system, which is not achievable in the hardware of any kind. So this is a software product. Yes, please.
And so even though the undercarriage is made up of different components, you present this as a single memory space for the operating system.
So this technology doesn't have persistency. That's a key difference. Fair. So because we have two memory tiers, one memory tier is our DRAM, we are not losing capacity of DRAM. So DRAM is exclusive cache, which is great. So we can always play with ratio of what the DRAM should be to what is Optane is. So we can extend the system by 8 times of the DRAM size. So let's say if you have 3 terabyte, which is your maximum size of a DRAM today in a dual socket platform, we can do 24 terabytes easy.
So in the environment you're showing here, you left the DRAM the same and just added Intel Optane SSD as storage? You've added storage as memory, yeah.
So effectively, it is a paging. It's a software. It's SCM software memory, and
the IMDT actually handles tiering of the structures across the DRAM Optane SSD boundary.
And Spark workloads is an example where, there are many kind of special overhead when you do storage I/O. So you always benefit of having all your data set in memory. That's why having another product technology which manages that and represents that big system memory capacity with Optane SSDs is really helping Spark. And it's not just about improving the runtime and getting the things faster with additional cost, but it's also doing that way more cost effective than if you would do that with DRAM. So not many servers today, especially for big data, designed with let's say 768 gig of DRAM, just because considering DRAM cost, it makes no sense. You better put another compute, probably, another server, complete server, rather than increase the DRAM cost. Yeah. If you do that in a cheaper market using that technology, of course, which has a trade-off with performance, always, because it's a hybrid memory solution, you can still do really good this type of applications and be cost-effective.
In this case, the application is running across 3 separate servers, and correct. The Optane storage is shared between all 3 servers, or no, each one has their own?
Correct. Application is running across 3 servers, like big data compute nodes designed, and Optane SSD is used in every of those compute servers as memory. So
that's not being shared across the 3 servers at all?
No.
But I'm really waiting for the next for the next round, because when this becomes Optane DC instead of Optane SSDs, the virtual memory engine that's running there doesn't have to do copies, it just has to do references. So the overhead
I was thinking they'd have all three tiers, so
Yeah.
DRAM, DC, and SSD.
But if you can put the persistent memory right on the
same price.
right on the memory bus,
Yeah.
the cost of accessing that memory is so much lower. And if you think about the way the virtual memory system in a computer works, when you access a paged out page, you not just have to access it on the slower disk, you have to copy it into memory, and that probably means you have to copy whatever was in memory back out. So there's a lot of work going on.
Data movement is always happening.
If it's persistent memory on the DIMM in the memory space, you can just access it directly, and you only have to do the copy when you've accessed it enough times to call it hot. So the penalty for accessing a paged out page goes down by a factor of 10 or 12.
Oh, wow. That's right.
There's just a lot less work to do.
You're correct. I have slide covering that.
Oh, so
But no, that's fine. You nailed that. The only difference that I agree with you that would be even an order of difference how quick you access the data. But that's not always represents the real application performance.
But this is referencing a larger memory space. It's actually a two-tier memory space as quote-unquote real memory, right? And you've got the virtual space, which is sitting on real SSDs out there, which is virtual memory. So as paging is happening between this pseudo memory space and this, the SSDs, that's all grand. But within this pseudo memory space, there's actually paging within that between DRAM and Optane SSDs.
But that paging, each of those page operations is much less costly.
And it's being done by the IMDT rather than the
than
virtual memory system.
Right, than IMDT or the virtual memory system, because that's still got to do, there's 10,000 instructions to get into and out of an NVMe SSD. There's 4 instructions to get into and out of.
Yeah, but it could be an NVMe SSD that's sitting behind the page pool.
Yeah.
So,
Not going into the details.
It doesn't make any sense yet.
How Optane DC persistent memory is architectured. Well, first of all, of course, different ways how you can use it. For this technology, because it's a storage, it's asynchronous device. So the beauty of that you can submit IO request, and you can do something else in the meantime. Especially when you have multiple Optane drives, like in this configuration, we had 2 Optane drives in the server. You can not just rebalance workload between them, you can benefit that devices can be asynchronous, and you submit I/O. You can do another course. Your system cycles are not really strong. You can still work on your system, and that can help performance overall. Even the device latency, let's say 10 microseconds, it doesn't mean that your system is constantly stopping for 10 microseconds. No. Even you hit the area which is an Optane, we may stop one single core, logical core, while other cores are still running because they may have access to the data which sits on the DRAM cache. That's the beauty of that. And it's available now. To take any actions for the first part of our presentation, read about VMWARE. It's really great stories. For many, it's not just a single story. It's really big how we can help to improve the performance of all flash VSAN solutions. Use that site, tryoptane.intel.com. It's a great resource with some free access to the technologies and free demos of the technologies. Get familiar with Intel memory drive technology, with Apache Spark, and we have many case studies at our Optane page.
So, Andrey, could you go back to this Spark thing again? I'm just trying to figure this out. What is the paging device beyond this IMDT space? Is that a normal SSD or what? So, I mean, in the 3X, without the Optane solution, there is a paging device sitting out there that there's no paging device at all.
Of course, look at that. There is standard storage where all your big data is located.
And what's that standard storage? Is that standard SSD?
Yeah, standard SSD.
7200 RPM device?
No. Well, say NAND-based SSD. which NVMe Express and sits for big data storage. And so you have to move the data between your limited memory that you have in a standard Xeon configuration, and
It'd be interesting to see this comparison with an Optane SSD as a paging pool versus an Optane SSD as an IMDT device. See if there's any distinct difference between these two. You know what I mean?
Yes.
Okay, I'm done. Thanks.
So one question on the same lines. I'm pretty familiar with kind of a packet walkthrough. Is there, maybe it's something you can't show us, but is there something like that for the way these different paging systems would work, where we could actually, like, maybe not today, but is there a way to do something like a packet walkthrough that kind of shows how, as a way of contrasting these different sort of flows? Is that a tool you guys use? And you can say yes, and we can't share it. That's fine. I'm just kind of curious if that's a better way to understand this than looking at performance numbers.
Because in one place you're doing what represents an IMDT paging structure kinds of thing versus a normal operating system paging solution here. And if they're both Optane devices out there, then they should be roughly the same, and maybe there's more efficiency in IMDT than in operating system paging. But it's not going to be, a factor of 5 times faster if they're both the same devices.
Yeah, I think I haven't included the study that we recently made for comparison between Linux paging versus IMDT paging.
Yeah.
And that's probably one of your questions that you had. Well, why would we do the special product that we cannot leverage what's included already into the operating system for free? So the reason is very simple. Reason is simple, but the explanation is long. At Intel, we have Open Source Technology Center, which is working on many open source projects, including paging in Linux. We have an amazing team who has improved the performance of Linux paging significantly, really significantly, and avoided many locks that happened previously. So it's all part of our recent kernels. Like internally in our lab, we are using kernel 4.16, which is no way in the current Linux distros. So we may say we are on the top edge of the latest additions to the Linux paging. However, unfortunately, it's really limited to what we can do inside paging. With Intel memory drive technology, we have special technologies for data prefetch, how you move the data ahead from the Optane drive to the system memory. And as Howard said, there's constant movement between Optane tier and DRAM tier. You have to do that in order to guarantee the performance. So, and one of these technologies, for instance, we can recognize the memory pattern we can recognize the application specifics. We can recognize structured, unstructured data, and can do prefetch, which is based on the real-time recognition with algorithm which is adopting in real time. So we can do that effectively, and at the time where application needs the data, it's already in the DRAM tier. This is not possible with paging today, and there is a huge memory hierarchy in the Linux kernel, which makes it impossible to do. So these type of limitations in memory management in the operating system basically forces us to think creative and to put all the paging stuff under operating system without any changes to it. That's critical because we don't need to tell our customers we want to go to kernel 4.16. Who would go to kernel 4.16 in the production environment? No one, except maybe some cloud customers. They will for sure. But that doesn't help. So including that technology under operating system, it's just a reasonable way to guarantee performance and compatibility. Hopefully I answered on that as much as I could. Thank you. I have to move faster because I have really nice stuff to share with you. That was nice, but this one is nicer because it's coming to the area where we're working with some technology companies to improve the performance of software applications for Optane technology. Why I'm saying for Optane? Because this is a kind of device which is only in the market that delivers that low latency. So the software enabling is significant effort that our team is doing. One of that is like what's recently happened in many software packages, and here I'm speaking about MySQL 8.0. it's just one of examples of collaborations where we did with MySQL development team, with Dmitry Kravchuk and his lead development at Oracle for MySQL 8.0. And they just spent the time to optimize the software stack for the storage software stack inside MySQL 8.0 to make it run faster, to be free from logs, to be really optimized for lower latency. Previously, they didn't really need to think about that because the software overhead was that and your media latency was that big. Now where your media latency is that small, everything that happens in your software is extremely significant. Another idea too that you can verify if you get your hands on the Optane drive. When we say 10 microsecond latency, sub 10 microsecond latency for 4K random I/O, significant portion of that, let's say at least 40% of that latency is distributed to the software stack. So the all hardware, PCI Express transport, ASIC, media, it's all like say 5-6 microsecond maximum. Everything else on top of that is your block layer, is your NVMe driver, and that is where your software really contributes a lot even at that level. Next one. Next one is interesting too because it's about Java improvement for I/O. So Java 10 has optimizations for direct I/O, so it's called direct I/O in Java 10. And that helps overall Java applications to benefit of a better efficiency storage stack. Again, didn't happen previously. There were many improvements done just to address the storage better than it was possible previously. Don't want to go to numbers, but just giving you ideas what's happening in the software industry. Example working with companies. I already shared VSAN example, which is awesome. But working just VMWARE, it's not enough for overall hyperconverge enabling in the market. So one of these examples that what we did with NUTANIX for their hypervisor, and again, example that we worked closely with software developers to optimize every time we do through their software layers what's happening in the hypervisor and how that can be improved. I have to be honest with you, we have many software tools which is not always software developers or customers familiar with. So as if you ever did any development in the software, you probably know Intel compiler tools, but there are great tools like Intel VTune, which is a application performance analyzer, which is in-depth solution to go into the software code and to find out the bottlenecks for memory, for CPU, for instruction set, how you can optimize, how you can go to the high parallelism. For years, we were looking for similar tool for storage that can be very easy to use. So we today have two tools. One tool is Intel Storage Snapshot, very user-friendly tool that can just run in the background and see what's happening with your storage, where is the bottleneck, what's the current workload, what is I/O weight, what is the CPU utilization. Honestly, I'm running it with almost every of my projects where I have an access to the system, so we can understand what's going inside the system instead of looking at system counters. Now I can look at the tool that visualizes everything from the same system counters. And it's a one tool. And another tool, it's called VPP. Intel is really good on acronyms. So this tool is included into VTune 2019, which is currently in a beta release. And VTune VPP is a platform analyzer that is extended version of a storage snapshot tool and can give you lots of details about what's actually happening with your storage. What's, for instance, your current queue depth utilization? Do you want to see that? Yeah, I want to see that. What is your I/O weight and all of that other stuff? What is your block size request? And these tools were really available for you and can help to see where we can improve the software performance.
So, ACROPOLIS is based on KVM. Does that mean you're ready for KVM as well, or is this purely based on what you're doing with?
That was purely based with NUTANIX, with VMWARE, because they have many IP layers. I would never say that what we did is available for KVM. We do very interesting work for KVM with SPDK team, and Anu can speak about that.
Okay.
Because I think that's really significant. Another improvement, how we can deliver better storage performance to the VM. That's critical. How you can bypass certain layers in hypervisor, how you can make it better. So that's part of SPDK project. It exists there.
Okay.
Again, in the interest of time, I want to make sure that I'm covering all material today.
And the optimizations that you did were software modifications to ACROPOLIS? Okay.
Software modifications. So our team is working closely with software developers to help them, first of all, to realize where the bottleneck is and to do some optimizations. In certain cases, we are really in a good situation where Intel has lots of power for software development. We have a huge organization which is doing already software development. We just need to point out these special places where we know that we can gain more advantages by just doing the software tricks, not doing any hardware. So resources. That's quite important here because, well, some links here, but just be familiar with SPDK and PMDK. PMDK is a key ingredient for developing for Intel Optane DC persistent memory. It's your full stack for application development. It has built-in emulators, so even you don't have Optane DC persistent memory in the system, you can still leverage PMDK and start software development right now. Obviously, without persistency, there are some limitations what emulator can deliver, but you can fully validate your application with emulators. That's really great because we know we have to enable ISVs and just as software developers with tools to start and to be ready to the hardware. Right.
Hey, Andrey, real quick. The free accelerate with Optane, what is that? That final resource right there?
Great question. I wanted to speak about advance. The tryoptane.intel.com is your website for ready-to-go demos. It doesn't give you an option to load your own data.
Yep.
So because obviously we just have like a predefined demos that you can run in real time on a bare metal. Oh, it runs in the Docker containers, but it doesn't matter anything. AccelerateWithOptane.com is our project for delivering cloud access to software developers and to key, let's say, end customers. So if you're an end customer, doesn't matter how big you are, and you have some crucial interest to Optane and you want to test it, we can provide it for your access for a matter of, well, 1 week, 2 weeks, or number of weeks, depends how the project schedule is. And so you can get access to bare metal server, which is available remotely with Optane SSDs inside it, as storage or as memory with Intel Memory Drive.
That'd be good for someone that's a blogger and wants to write about but doesn't have access.
Oh yeah, absolutely, yes, sure.
Thank you.
Let's speak about innovations, not just necessarily in the Optane space. So finally, I'm moving to talk about ruler. What is ruler concept is and how we see evolution of a ruler system and why ruler is not ruler anymore. It's called EDSFF and so on.
How is it called?
EDSFF. So
We like acronyms.
oh yes, Intel is very good at that.
Short one as well.
I already mentioned that. So that happened as evolution to the form factors. That was, to me, that was an obvious reason that we were limited with the form factors available for the storage today. Because they either came from the adapter cards, where we have to put all the NAND components onto the PCI Express adapter card and load it into the platform, and where we have limitations for density, where we have limitations for airflow, and other limitations which are part of our PCI Express cards. Or then we decided to go with U.2. U.2 is a great form factor to promote PCI Express and to deliver PCI Express into the high density configurations. However, all of them are coming from devices which were not originally designed for storage. So not for SSDs especially. And so let's say, thermal efficiency of these devices, it's optimized for hard drives. Of course, you can load in 2.5 inch, all your plates there. So for SSDs, what it means, well, it's a quite heavy brick, first of all. Typically inside like a 15 millimeter U.2 drive, you have two boards side by side. So it's not always the most effective cooling, because some components facing outside, some components facing inside. So to guarantee the same cooling efficiency to all components inside their U.2 SSD, for instance, we have to have significant airflow coming through that SSD. So that basically means we have to spend a lot of money for cooling SSDs, especially if they're in an environment where you have lots of writes, and that's typically where NAND-based SSDs produces the most heat. So doing something innovative in that space, the serviceability which is required for all storage components, we came up with a plan of a ruler idea. So ruler SSD, it's about 1 foot SSD in original specification, and it's a single PCB design. So you have one PCB board, which faces components both sides of this board, and it's inside the enclosure. So it's optimized for cooling, it's optimized for overall surface size, because we can put many of these media components inside ruler, and so we can do higher capacities that we could do in U.2, for instance. That was original. And that's what Intel introduced as Intel ruler concept. And we were quite successful with that, also delivering these products from Intel exclusively, and with our partners like Supermicro, for instance, for delivering the JBOD configurations. The problem was that we needed to scale that to the mass market, and we had to speak to the whole ecosystem, to the whole industry, to make it industry certified. That's where the name EDSFF comes from. So EDSFF is industry standard for ruler design, which was actually changed for goods, and so it has slight changes from original specification that Intel only produced, and it's extremely flexible in what you can deliver with that design. So in this design, let's have a look here. We have, let's say, at least 3 basic form factors. One is long ruler, so it's a same 1 foot, 9.5 millimeter. Another one is 18 millimeter, still long, but it's, as you see, it's basically a fat version of that. And one of that is called short. Short is caseless, so you don't see case on that. It looks to you like, well, it looks like M.2 drive. Well, actually, it's not M.2 drive, it's a ruler drive. The significant difference between M.2, for instance, design, is that, it's a hot pluggable, it's a single power rail, and it's optimized for performance. So it's slightly bigger than M.2 drive that allows us to put more components on it and deliver higher capacities that all M.2 designs currently have, and be not limited in their power like traditionally M.2 SSDs are really limited. So 3 designs. Now combining them and designing the special systems, you can go either to the storage, where you can load, let's say, 32 rulers in front of your system, and technically you can build 1 petabyte in 1 unit if you have 32 terabyte rulers. Or if you don't need that much capacity and you still think about serious compute inside your server, you might decide, okay, I will go with short rulers because I don't need to have that much capacity, and I can put 48 of them, or I can put 32, or I can put 8. Only design matters. So that gives you an idea what
gives me enough room in a one-use server to actually have processors and memory and maybe an add-in card in the back.
Oh, yes.
Where the long ruler takes up most of the case.
Absolutely right. So think about that. If a long ruler design, let's say it's 25 watt in a peak, in the average power consumption that we use for writes for highest capacity, and if you have 32 of them, wow, it's amazing that you spend like 700 watts just in front of your system for your storage, and you have still to have some thermal headroom for your dual socket CPUs, especially if you want to have one. That is actually the reason for this 18mm ruler, because in fact, it's pretty much the same design, at least in our implementation, in Intel products, but it has higher surface area, so it has bigger heatsink. So if you don't really need 32 rulers, but you're okay with 16 rulers in your system, 16 long rulers, you don't need to have that high airflow, and it can be more efficient from a thermal perspective because heatsink area is bigger, you don't need high airflow, and you have enough headroom for your real CPU compute after that rulers in front of your system. At Flash Memory Summit, we really introduced a lot of innovator companies who already presented their ruler designs, short and long, with us in our booth. But let me explain why ruler is important overall. Ruler, first of all, is important when we introduce their high-capacity storage technologies, such as with NAND-based QLC SSDs. Why is that important? Because we really, with QLC, we are approaching the area where we are coming into what typically was a hard disk market, where we try to replace hard disks not just by the price, by serviceability, failure rate, power consumption, and overall system design and capacities. So not just speaking that 32 terabyte ruler SSD is higher than any available hard disk. Well, we know the capacity of hard drives is not really growing up last 2 years, well, 5 years. That is also your path to make your system design is cost effective. Why is that? Basically, when you have so much density inside the single ruler design, you can, let's say, go at least as twice capacity of U.2 drive because you have that many surface and you can put that many components onto the drive. That helps you to make your storage design is cost effective because you don't need that many PCI Express switches, for instance, comparing to U.2 drive where you have to put so many PCI Express lanes to aggregate all available devices. Here you just have a single PCI Express Gen 3x4 coming from a long ruler. Design spec allows us, first of all, go to PCI Express Gen 4, Gen 5. So by the connector, it's already compliant to Gen 4 and Gen 5 specs. There are also additions to the specs where your ruler can not be Gen 4, it can be Gen 8, or if it's wider. So there are many tricks already included into that extended specification for EDSFF, which makes perfect sense. And then when you aggregate that many rulers based on the QLC media, you really approaching the point where you can compete with the hard disk technology for the cost. First time ever for the cost. No one questions performance. No one questions performance per watt or but the cost, overall cost of a storage is really key here because we are going into that area. All right. Some examples here. Some of them I can really share with you. Some of them are still work in progress. This one, which is currently work in progress, but we have full clearance to talk about that. That is with Tencent, Chinese cloud company, really innovative and moving ahead of a time to new technologies. So the way they redesigned their distributed file system is from having NAND-based SSDs for their frontier caching for their hard drives. They redesigned it to leverage just all Intel QLC SSDs instead of having that two-tier approach. And for them, they say that they can improve IOPS overall. They can improve within the budget, they can really dramatically improve scalability of these configurations because it's a storage design, it's high storage design. All right. A little bit more about IMDT. Do we want to talk about IMDT, or we covered that previously with Apache Spark? If you have any other questions about Intel memory drive technology, or you may decide that you want to test it, so you have a resource, we have a cloud available for you that you can test it, you can run your own applications. As said, it's a hybrid memory, so it may work for you, it may not work for you at all. There are many applications which are really heavy to consume all available DRAM bandwidth with very small flops in the system, so all you need is just DRAM. It's not a way for hybrid memory.
The best practice is to have 1 to 8.
That is a max.
Okay.
The beauty of a technology that you can mix and match. We have certain customers who said to us, we want to run in the best efficiency as possible for the money, and we don't want to sacrifice our quality of service for our database, for instance. What if instead of 1 to 8 ratio, we put 50% of DRAM and 50% of Optane? And that's possible because it's fully supported. And so the idea is, of course, as more your DRAM cache is, so as more closer performance to the DRAM, unfortunately, your price goes up. So playing with the application efficiency is really key here. That's why we have these systems for remote access for you. So if you have some application codes, in addition to what we already tested and published, like for big data applications, for HPC, for really great stories for KVM, how you use it in a virtual environment, in virtualized environment. Yes, we have this available in the cloud service, and you can test it on your own. All right. So, and finally, why it's different from Optane DC persistent memory? Well, obvious reason, because Optane persistent memory is not yet here. It's Optane persistent memory by the paradigm that included into the product, it's more towards to the DRAM. It sits on the DRAM slot, it goes next by the DRAM in the configuration, but the overall idea of the product, the most beauty of the product is persistency, which doesn't exist in a software version of that, because we cannot manage two-tier solution. Even Optane SSD is persistent. DRAM is not persistent, because if you shut down the system, your cache is gone. You lost all your data. So there are choices. And these choices will be available at the time of DC persistent memory and later on. We are not trying to introduce one technology and shortly introduce another technology. It's just a different markets for these technologies where you can live with paging and where you need the full hardware configurations. And so you have choices, and consider IMDT, Intel Memory Drive technology, as a first step to that hybrid memory technology, because it's really interesting how you can change your mind and thinking of.
Are you going to change the capacity of DC versus Optane SSDs? I mean, is it going to be a smaller capacity configuration?
Correct.
Is it safe to kind of take from what you're saying that essentially these options primarily exist due to the timing that these technologies are coming out?
I wouldn't say that.
You wouldn't say that at all?
I wouldn't say
Okay,
that.
okay.
They just designed for different reasons. Optane DC persistent memory is time to market to new Xeon CPUs and fully supported from a common stack of their CPU. While the software product, it doesn't really need to be connected to any CPU technology. We can run on any Xeon E5 since version 2. All we need is VTX and VTD. And these are two virtualization technologies, and that's it. And of course, working NVMe SSDs, done.
The IMDT software is in one of these. Which one of these components is persistent memory development kit, or where is the IMDT technology software?
It's separate. It's a separate commercial product. It's available as a separate license. Comes on top of Optane SSDs, or comes pre-configured. Already, so you have two options. You can buy Optane and use it as storage, and maybe later you decide to convert it to memory. Or you can buy the SKU that already has pre-activation license.
And it's compatible with all operating systems, Linux, vSphere, Windows.
Great question. Don't want to interrupt you, but just want to say that we work with all major Linux distributions. We do not run on Windows. We do not run on VMware. we run on KVM, so KVM can be another second-tier hypervisor on top of that, which makes really interesting solutions how you can create a dual circuit configurations with so many terabytes of memory, and how you can manage your VM pool based on the, for instance, quality of service that you need to guarantee to customers. Oh, wow. It's really great stories because we have customers using that exactly in that environment where we say, okay, what if I have 1,000 VMs which are active, but we don't need to guarantee quality of service, or we don't care how exactly they work. That's an option.